Okay, we're going to look now at Chapter 3, Part 3 of the 3 parts we're gone through this chapter. This should be the only chapter that we have 3 parts. And the last 2 topics are sorption and reaction kinetics, and we really do need to cover them because they come up again and again in the rest of the book. So sorption is a word that's meant to encompass both adsorption, A, D as in dog, and absorption, A, B as in boy. And absorption, the second one, is also called partitioning. So adsorption is the accumulation at the surface, whereas absorption is the accumulation in another phase. Most often we're talking about organic matter of the soil. So it's sort of like it's going into a liquid organic or a mesh of organic. Both are equilibrium reactions. That means that some of the sorbing species remains in the water. The more hydrophobic the chemical is, the more will go onto or into the surface, and the less will stay in the water. But some always stays in the water. So we describe sorption using these mathematical models, simple models really. Usually we use a linear model here that says that the sorb concentration is a function of a partitioning or distribution coefficient K and the aqueous concentration. So we do get some funny units here because the Q is now a sorb phase, so it's the amount of chemical on the solid surface. So it's got sort of like mass I per mass solid. There's a second equation that we use because sometimes the sorption of behavior is nonlinear, and this Freundlich isotherm allows for nonlinearity by raising the C, the concentration, to an exponent. It's kind of a funny exponent, 1 over m, and that's 1 over n, and that's sort of a legacy effect of where this came from, which was the gas absorption literature. So just think of it as a number up there, C raised to a number. So this is what the model looks like when that 1 over n, that funny exponent, is 1. Then you just have the linear isotherm. And then sometimes it's less than 1, and you get this nonlinear concave down shape. Those two are the common ones. This other one is less common, where you actually find something that's sort of not wanting to sorb, and then all of a sudden it sorbs a lot. So sorption can be good or bad. It depends on the circumstances. Let me give you some examples. So it would be bad if the chemical's in the ground and we want to get it out. This top picture shows a contaminated plume or body of contaminated water in an aquifer. And if we want to get that out, it's going to take a while because it's going to be sorbed to the solids down there. So we'll keep pumping water out that has small amounts of the chemical in it. Then it will desorb or come off the solid a little at a time and slowly come out of there. The good news is that once you pump it out, you can put it onto something that sorbs very strongly, like activated carbon in this case, that comes in these canisters. And you would pump it from the groundwater, for example, up here and into these canisters, and it would sorb on there. So you could get a lot of chemical into a small volume of carbon. So sorption is a little more complicated than some of the other thermodynamic properties that we looked at, solubility or vapor pressure, these sorts of things. Sorption depends on the chemical and on the solid, the sorbent. So we often have to measure it, and we measure it by doing what we call isotherm tests. And isotherms are basically little vial tests where you put some soil, some water, and dissolve some of the pollutant that you're interested in into these vials. And so what you do is you get these dots. So each one of these dots would be one of these soil samples, and then you fit a line through these dots, or you fit a curve if they look nonlinear. These ones look fairly linear, so we're sort of just fitting a line through them. So the slope of the line there would be the K value for that. So in the textbook they have an example in table 3.1, so you can look at that and you can see how they do a test. In the textbook, they have a solution of, they all start with 150 milligrams of MTBE. They put them in these quarter-liter bottles, 250 mils, and they also add some activated carbon. And then they wait for them to equilibrate. They kind of mix them up and let them sit there for a while. Note in this one, they add the same chemical amount to each one, but they have increasing amounts of carbon, so you should get a lower concentration in the system. So here's the lower, this one's the lower concentration at equilibrium. And then you actually have to calculate the Q. It's actually very difficult to measure the Q. If you think about it, the Q's in the water and it's stuck on the solid, so you can't really pull the solid out of there and measure it. This last columns, they just take the log of each one, because if you take the log of both sides of that Freundlich isotherm, you get a linearized equation. So you get this. So if you link sorption to organic matter, that's been, some people have tried to do this in order to avoid these isotherm tests. Isotherm tests are a lot of work. So they look at chemical properties that are connected to a chemical's hydrophobicity, or how badly that chemical wants to get out of the water. So some likely suspects are solubility, or the octanol water partition coefficient, KOW, works pretty well. So in this case, they would take a bunch of different combinations of soils and chemicals. So each dot here might be a different soil and a different chemical, and they put them on that line. So maybe if these dots line up perfectly vertically, then you're talking about the same chemical, but it looks like most of them don't. So these are all different chemicals and different soils, or maybe some similar soils. But if you do the isotherm test with all of them, you get this cloud of data points, but they have a trend, and you fit that trend, you get a pretty good regression, 0.91 R squared. So then you could use this regression to try to predict the K for other chemicals. So we were talking about sorption. Now let's talk about reaction kinetics. So before we were talking about equilibrium reactions, where the reactions proceed rapidly, or we've given them adequate time for equilibrium to be achieved. So reaction kinetics pertain to the rate at which the chemical reactions occur. Sometimes this is important because a lot of reactions we're doing, we're not really doing an equilibrium reaction. We're actually trying to make some new chemical, or we're trying to degrade a chemical. For example, here you're hydrolyzing this ethane molecule and turning it into a alcohol. Or in many cases we're trying to degrade a waste, or here we're trying to oxidize a waste with oxygen and microbes and get it down to CO2 and H2O. Or radioactive decay, certainly going in one direction and not really going to come back. So reaction rate laws, you can sort of infer them by looking at the stoichiometry of the reaction, but the text maybe oversells that a little bit. Sometimes that works, but other times you have to do some studies and just see how fast the reactions go. So kinetic studies are needed, but we're not going to do any kinetic studies, and we'll always be sort of given the reaction rate in our problems. And for us, there's basically three kinds of rates. The zero order rate means the rate of reaction is constant, so the products increase while the reactants decrease. Both move linearly, it's just a constant rate of change. First order rate is a little more interesting because you get an exponential decay of reactants and a growth of products, because the reaction rate is actually proportional to the amount of chemicals, the amount of reactants present. The second order rate depends on the concentration of two reactants, or it could also depend on one of the reactants to the second power. So first and second order both depend on the concentrations of the reaction, so it's a little more interesting than the zero order. And the first order is probably a little more common. The pseudo first order rate is kind of a second order rate, but it behaves like a first order rate if one of the reactants is constant. So if you think about a reactor where you're always adding a chemical, then it could be a pseudo first order rate, even though it's really a second order rate, because that input concentration would let the reactor always kind of have the same waste concentration, for example, but it would be degrading. The new waste would come in to replace the waste that's degraded, and you'd end up with the same constant concentration in the tank. And that's the way we run a lot of reactors, and you'll see that when we start to do our reactor theory in just a week or so. So half-life of reactions is difficult when you get a reaction rate constant to get a feel for how fast the reaction is happening. So a half-life is the time required for a concentration to be half the starting concentration. So just simple math will tell you that for a zero-order reaction, this half rate constant is equal to half of the initial concentration divided by the rate constant. And for a first order reaction rate, you've probably done this before for like an exponential decay type of problem. In this case, you get that the half rate is equal to the log of 1/2, which is this 0.693, is simply the natural log of 0.5 divided by k. Temperature effects are important for kinetics. Higher temperatures result in faster rates, and we usually use, if you remember from your chemistry classes, the Arrhenius equation is used to adjust rate constants if the activation energy is known. So you would be able to find the K from 1 based on the temperature change. For biological processes at environmental temperatures, you'll often use this more empirical expression that's based on Arrhenius, but it's just been simplified, and it uses this capital theta term, which is usually just a little bit bigger than 1, depending on what kind of process you're using. And so if you know the reaction rate at one temperature, you can easily get the reaction rate at another temperature just by raising that value that's around 1 to the difference in the temperatures. So wastewater treatment plant design, the plants have roughly the same temperature of the water entering, because underground pipes kind of insulate it, so it doesn't have a long time to change temperature. Many of the plants are exposed to weather, though, so you get large seasonal changes. So you might have, in these big open air tanks that you see here in the picture, you might have a different temperature in the summer than you'd have in the winter time. So what temperature would you use to design it? Well, if you think of it from a reaction rate perspective, we know that the rate is going to be faster in the summer and slower in the winter. So you'd probably design for the winter conditions, because the slowest rates, it still has to get the job done that you need to get done. You need to remove a certain amount of waste. So if you design for the winter conditions when things are slow, it'll just work better than it has to in the summertime. So that's a quick overview of sorption and reaction kinetics, and we'll do some lots of work with these, so we'll get to know them pretty well.